Okay, this part 2 of your development length has to do with what is called the cutoff points. I'm doing this because any of you are going to take the advanced concrete class. I mean, I don't want your professor to say, "Hey, you never learned about this, right? Why you were not taught this?" So the concept is pretty simple, but there's a lot of little detailing that goes with it. Okay, and really, what it is, and this figure, it is in your code, right? This is the part of a positive envelope, right? And this is a negative envelope, right? So that's why the point of inflection do not coincide in there. But what it shows is that if in a negative value, for example, you decide to cut, right? You decide to cut some bars at this location, right? So that would be your theoretical cutoff point. Okay? That's where you are. Ideally, you want to cut, right? Then what it says is you cannot cut exactly there. Okay, you need to add at least D or 12D sub B, and then this becomes your real cutoff location. Not only that, the distance from the face to that cutoff location has to be greater or equal than the development length. Okay, and so that's important. Now, if you cut something past the point of inflection, you need to add the same thing, D, 12D sub B, but you need also this ln over 16. And this second group of bars is critical now that your development length also be satisfied from the theoretical cutoff point of the previous bar. Okay? And the same for the positive, okay? Same idea. You got your cutoff theoretical point, you need to add D or 12D sub B to do that, but from the critical location of the other bars, you need to maintain LD. Okay? The same here, see? This is your maximum moment. If you cut some bars, theoretical value, you add D or 12D sub B, but the total value has to be greater or equal than your development length. Okay? So what is this cutoff thing? Okay, let's look at this. I think I may have one here that I did a long time ago. So here is your simply supported beam, right? Maximum moment, that's your MU max. And you decided, okay, I'm going to put 5 number 8s, that for my maximum moment. Obviously, you don't need the 5 bars all the way to the end, right? So at some point, I'm going to cut 2 of the bars, and I'm going to leave 3 bars going through. Yeah? I could have cut 3 and leave 2, but in this case, I'm cutting 2, and leaving 3. So here, then I have 3, and here I have 5. Okay, so this point where the moment in the diagram, okay, the moment in the diagram equals the design strength, right, of 3 number 8 bars, that's your theoretical cutoff point. Okay, so in other words, the design strength corresponding to the bars that remain, okay, not the bars that you're cutting, the bars that remain. So you have 3 remaining, so the design strength of the 3 bars remaining has to be equal to the MU at that particular location. Okay, so that's your theoretical cutoff point. From there, you have to add the D, right, and the 12D sub B to the bar that you're cutting. But the distance from the maximum location to the end has to be greater or equal to the development length. Yeah, that's it. All right? That's it. All right? So, there is a theoretical cutoff. That point means that the design strength of the bars that remain has to be equal to the value of the moment at that particular location. They have to match. Okay? You cannot cut your bar of the theoretical cutoff. You have to add D or 12D sub B. But the distance from the maximum case to the end of the bar, past the theoretical, okay, this is the end of the bar, has to be greater or equal than the development length. That's true for positive or negative. All right? So that is the idea. Now, why do we need this extra here? Why don't just stop there? I mean, that's the theoretical value. Well, thing is, moments change. Remember, you have different load cases. That's one reason. In there, another thing is that, remember we talked about when I show you development length and all that it takes time for the stresses to go from 0 down to the Fy, right? So remember that at this tip, 0 stress, and things growing until you get to Fy. So it takes time, right? So the moment then is varying linearly until it gets to the maximum value. Okay? And so you have to give it in that distance, that extra distance, right? So the stresses will grow and finally reach your yield value. Okay? So that's one reason for that too. Okay? So going back then here, so these are the drawings. As I said, this is in your code. So you look at your code right here on 9 on beams 9732, right? Yeah, you have the same drawing, okay? And they show you your negative and your positive and the critical values and all that. So all this is here in your code, okay? So you have it. Okay? All right. This is just a larger version. Okay, so what do we want to do then? There are some requirements, the special things that we need to satisfy. Now, if you cut bars in a tension zone, which is this case that I show you, right? You're cutting bars in a tension zone. Then there is a problem of potential shear failures. Okay? So to do that, to cut bars in a tension zone, you have to satisfy that at the cutoff point, okay, VU has to be less or equal than 2/3 of phi b sub n. For number 11 bars and smaller, no, the continuity or reinforcement requires that an area of at least double the area required is provided. It has to be 2 times the required value for flexure, and VU less or equal now than 3/4 of phi b sub n. You need to provide either additional stirrups or hoops are provided in excess to that required for shear. So you may have your nice spacing. Remember you did, everything at 10 inches, very nice. Oh, you do a cutoff, you may have to put more stirrups there in that area, okay? And those may be at 5 inches or 4 inches, depending on what you need, because you need to satisfy this requirement, you need to satisfy that requirement, okay? Now, the area of additional stirrups or hoops shall be at least 60 BWS per Y, and the spacing should satisfy no more than this, where beta B is equal to the ratio of the area of steel terminated to the total area of steel at the cutoff point, right? So if we go back here, then it will be the area of the steel terminated, right? So we're terminating these bars, so that's the two bars, right? And the total value is 5. Okay. Okay. So what we're trying to avoid is then the right of the tip you develop a shear crack. Okay. That's basically what you're trying to avoid by doing that. So we're going to skip all this for now, and let's do one example here that deals with this one. Okay. That doesn't look good. The interior beam that we did this in example A5, right? And it was also on your exam, right? The same thing. It has 3 number 9s. So what we're going to do is we're going to cut the middle bar, okay? Wherever we don't need it anymore. Now, since we know that, first thing we're going to find is the development length, the number 9. Okay. They are giving us also the stirrups, 1 and 2, and the rest is 6. That's what we normally design for, right? And slab thickness is also given. Okay. And we're going to cut the middle bar and see what it is. But we're going to find the theoretical cutoff and then the final length. Okay. So even though this one is a positive diagram, what you're going to find is, what we're asking is, find the development length, 1. 2, find the distance to the cutoff point, and then find the actual cutoff length. Okay? So that's what we're looking for. So let's do that. So first, development length, I mean, we use the same formula that we've been using already. These are negative bars. So top bars, we're going to assume they got 12 inches below. And let's see, you do. I mean, this is 18. So yeah, so chances you have more than 12 inches below, right? And therefore, then, you can use a value of 1.3. Then the rest of the values are ones. Okay? The CB, let's check it. C sub B, top surface to center of bar. Remember, we use a distance of 225 here because we don't want to interfere the slab bars with the beam bars, right? And so we did that. And so we had a 225. Then to that we add the stirrup, and then half of the bar. That gives us 356. Then from the side, on the side, notice that we got the slabs. Okay, so there is nothing there. Okay, so that's protected. So we don't have to worry about the side. And then half of center to center spacing. So we find the S first, and this formula was given to you, right? You have it in your formula sheets. So this is the center to center spacing, right? And now we take half of that, that's 219. That controls over that number. So C sub B is that. Okay. The area of the AT bar, well, we only got 2 legs, right? And the spacing is controlling, so it's going to develop that crack here in there. So you can conservatively do only 1 leg, or you can do just the 2 legs. Okay? In this particular case. Oh, sorry, I'm here on the top. Right? So we have really a crack here developing, right? And so you can say that it's only one leg if we use that method, right? Or you can use the 2 just to be conservative. Okay? So I did 2 here. I get a value of 147. Okay? The value of N1 was used because only 1 bar is being cut. Okay? So this is the number of bars being cut. Right? And S is the spacing of your stirrup. Okay? So that gives you 324. So that puts this at 2.5. Now, if you would have done here the 0.11, which is also a valid number, since you only had the vertical option, right? And this is where we're things are not that clear. Okay, some designers go for that, some designers don't. But that's all you're cutting. I mean, you're only cutting 1 leg. So you do 1 leg, it would be 40 times 0.11 and divided by 6. That would be 0.73 plus 2.19, right? And you divide by 1.128. So it gives you 259. So you're still going to use 2.5. Yeah? So I think I'm going to do that. I like that better. because that goes with our theory that you have one vertical crack, right? Then you only have one leg crossing it, so you should use one area, and this will give you 0.73, and with that we get here 0.73. So at least we are consistent with our theory and not varying that. Okay, so we still use 2.5. I mean, it doesn't change the result, but it could have changed it, right? So we do that, we get 37 times dB multiplied by the diameter of the bar, number 9. So we need a development length of about 42 inches, is greater than 12, so we're good. So development length is 42. Okay. Now remember that the code allows also for 0, right? So the code says, hey, you can assume all these things go to 0, right? You can do that. If we do that, then this is 194. Because this is a more conservative approach, you're going to end up with a larger development length, right? And that would be 54. Okay. So notice that I could have simply skipped, right? I could have simply skipped this calculation here, right? And we make a 0. And this is why this thing about the 2 legs, 1 leg, and all that, people just go and say 0, right? Make it simple, because it's conservative. Okay? You're getting a longer development length. So you have that option. Okay. So either you do this one that requires more calculations because you have to find your KT's bar, or you are conservative, put a 0, and that gives you a longer value. Okay. All right. So what do we have then? So this means that from the critical section we will need at least 54 inches. Okay. Correct. Okay. Now let's find the cutoff point. Right. So again, we need to find our effective flange width. Right. And some of you were in the exam. I mean, was you understand the center to center spacing is your tributary width. Okay. So, but you were missing that one quite a bit. Okay. Several of you. Okay. And then this is the LN. This is the span of the beam, not the clear span of the slab, right? So yeah. So we look at these numbers and we take the smallest, 50. We check for AS minimum because we're cutting 1 bar. Remember, we're cutting 1 bar, we're leaving 2, right? So we need to make sure that we're satisfying minimum there too. So we check. We need to use this one because doing a cantilever, so tension, flanging tension, you have to use a different value for BW, right? And so when you pick it up in the exam, very good, that was excellent. So you get your value, so 145 control, so I need 145. Since I'm cutting 1, there are 2 remaining, and that area is equal to 226. Is more than minimum, yes, I can cut. Okay. Now I'm going to find the moment, the design strength that corresponds to the remaining bars. So there are 2 remaining. I'm going to find my A value, find my C, find my D sub T, check my ductility, right? Find my design strength. So this is the design strength of 2 bars. Next, right? Next, see, I found already, even though again this is a positive, not a negative, but this is a positive. So what we have found is the strength of the remaining bars. Okay, that has to be equal to the MU in your diagram, right? Okay, so my remaining bars were 2 in that example, so we use the strength of 2 bars. Now I need to make this one equal to the moment in my beam. Okay? Well, the load, we had it in the example, because it can deliver, right, is WL squared over 2. Right? Since we're coming from the tip going to the support, right? Then I've solved. My mu happens to be a z squared. That equals to this, so my z value is 1167. So I can almost cut it right at the face, very close, right? And I can eliminate. So that means that thing number 9 was a very conservative design, okay? Very conservative design. So I do 12 minus 1167, gives me 0.33 feet. That's only 4 inches. Okay. This one is the theoretical cutoff length. At 4 inches from the face of the support, I can cut that bar really, right? Because it was conservative design. All right, but you cannot cut really there. That's your theoretical value. Now you need to add to that one, right? The D or the 12 D sub B. Okay. My D 1481, my 12 D sub B 1354. This one controls, so I add that one to this one, 17.5. So I say, okay, 18 inches. So I can now cut it until I get to 1.5 feet from the face of the support. Okay. So let's go back here. Theoretical cutoff, 4 inches from the face. Okay. Real cutoff so far, 1.5 feet. But there's another requirement. From the critical location to the end of the bar that you're cutting, you should have the development length. Oh, okay. So that means that you use the conservative approach, you need to have at least 42 inches. You use the conservative approach, you use the actual design approach, right? Using your values here is 42. You use the conservative approach is 54. Both of those values are greater than 18 inches. So you need to decide which one you use. Right? Do you want to use this one or do you want to use this one? I go conservative. So 54. Okay. So I need then, instead of 18 that I found, because of my development length, I need 54. Okay. Is my final cutoff length. So I need to cut it then at 4 feet 6 inches. So going back here, so you see the process, right? Theoretical cutoff was about 4 inches. We had the D and the 12 D sub B that put us at 1.5 feet. But there's another requirement that says that from the critical value to the end of the cutoff, you need to have a distance equal to the development length. That one was 54 inches. So that put at 4 feet 6 inches. And that's where you can cut your bar, your number 9. Okay? And that's all I'm going to cover on this lecture. Okay? Nothing else. In there. I think that's, yeah. This other example right here is a more complex example. So I'm going to touch that one. Right? Only that. All right. So that means then that we can